Alright, so 6.3, we're going to keep talking about angles and trigonometric functions. But we're going to take our perspective on angles and change it just a little bit. So in geometry, as we've been talking about, an angle is the union of two rays or segments with a common point called the vertex. So this point right here is our vertex. And then we have two rays, which are just line segments, either infinite or semi-infinite. And then we would talk about the angle in between those two rays, which would be this, which would be the angle theta. And if we measured the angle this direction, or if we measured the angle this direction, we would get the same number, and it would always be positive. So for mathematics, we need to define a positive orientation for angles, and we're going to coordinatize them using our standard coordinate system to give us some reference. So let's take a look at our next definition. So in trigonometry, we will think of angles as a rotation. The rotation will be measured counterclockwise from the positive x-axis, with the vertex being at the origin. We're going to define a counterclockwise rotation to be positive and a clockwise rotation to be negative. So let's draw a picture. So if we take our Cartesian coordinate system, and we have a line segment, and this is going to be our terminal side, we would have this angle right here, theta, and theta would be positive because it was a counterclockwise rotation from the positive x-axis. Similarly, if we had an angle like this, so the angle alpha, this would be a negative rotation because from the positive x-axis we went clockwise. And once again, this would be the terminal side. Let's take a look at our first example from our handouts. So we wish to graph the following two rotations. So 135 degrees and negative 225 degrees. So first thing we need to remember is that if we rotate all the way around, so if I were to start at the positive x-axis and go all the way around to back to where I started, that would be a rotation of 360 degrees. So if I were to rotate from the positive x-axis to the y-axis, well, that would make a right angle, so that would be 90 degrees. From the positive x-axis to the negative x-axis, that would be 180 degrees. And if I went from the positive x-axis to the negative y-axis, that would be 270 degrees. So to get to 135 degrees, if we know this is 90 degrees and this is 180 degrees, 135 is exactly halfway in between 90 and 180. So our rotation of 135 degrees would be out here in quadrant 2. And that would be our rotation of 135 degrees. So we started at the positive x-axis and we went counterclockwise because our angle was positive. For our next angle, we want to go to negative 225 degrees. So for a negative angle, that means we are going to rotate clockwise. So then this would be negative 90, this would be negative 180, and up here would be negative 270. So 225, once again, is halfway in between negative 180 and negative 270. So our rotation would actually land in exactly the same place. And that would be a rotation of negative 225 degrees. So we say that the angles (135 degrees and negative 225 degrees) are coterminal. So when we're talking about rotations, we see that we can have two different angles that have the same graph or the same terminal side. And in fact, if we think about this, if you rotate 360 degrees, you went around once. If you rotate 720 degrees, that would be you going around twice, and so forth. So we're going to have many representations for any angle in this system. So here's another definition. If two angles or rotations have the same terminal side, we call them coterminal angles. All right, so now we have a theorem involving our coterminal angles. So, theorem: two angles are coterminal if their difference is divisible by 360 degrees. So if we look back at this example, we're told that two angles are coterminal if their difference is divisible by 360 degrees. So if we grab our calculator, we can check this. If I go 135 and I take away from it negative 225, I get 360, which is obviously divisible by 361 times, but it also works in the opposite order. If I go negative 255, or 225, and I take away from that 135, this time I get negative 360, which is also divisible by 360, negative 1 times. And this is true for any two coterminal angles. If you subtract them, their difference will always be evenly divisible by 360. So it's now your turn. So go ahead and try your U try number 1. So for U try number 1, it says find 3 coterminal angles to 195 degrees. All right, so to find coterminal angles differ by 360 degrees. So we can just take 195 and add 360 degrees to it, and that will give us 555 degrees. If we wish, we can just do this on our calculator by making a table. So we start with 195, and then we go plus 360x, and then if we go second table, we'll see for 1 we get 555. Our next coterminal angle would be 915. And if we scroll back this way, we'll notice that we get some of the negative values. And so every angle is going to have an infinite number of coterminal angles. So from this table, we see that there are quite a few. We have negative 885, negative 525, negative 165, 195, 555, 915, 1275, and so forth. So it's worth noting that every coterminal angle has the form as we saw when we made the table, 195 degrees plus 360 degrees times n for every integer n. So the way we are going to write this, so this phrase can be abbreviated as for n in z. So we make this funky blackboard Z looking thing, and this stands for the set of integers. And what we mean by Z as a set is that it's all the positive and negative whole numbers and 0. So basically what this is saying, like we saw in our table, if I take 360 degrees and multiply it by any positive whole number or any negative whole number, it will generate a coterminal angle. So to be very, very explicit, what this phrase means is that it is n, and the red means in the set, and then this is our symbol for the set of integers. So when we see that symbol, or this chain of symbols, that is what it translates into. And we'll have use of this later, and we'll use it as we do some other things. So we have another definition, which is about complementary angles and supplementary angles. So two angles are complementary if when we add them up, their sum is 90 degrees, and two angles are supplementary if their sum is 180 degrees. So in this first example, it says, find the complement of 63 degrees. Well, by definition, we know two angles are complementary if their sum is 90 degrees. So we would have 63 degrees plus its complementary angle would have to add up to 90 degrees. So then solving that equation, for x would tell us that the complementary angle to 67 degrees would have to be 27 degrees because 27 plus 63 is equal to 90. All right, the next one's for you guys. We're not going to go into rooms for this one. So go ahead and find the supplement of 87 degrees. All right, so to find the supplement of 87 degrees, we need to find an angle, x, when we add it to 87, that gives us 180 degrees. So we minus 87, we minus 87, and we get x is equal to 93 degrees. So the supplementary angle to 87 degrees is 93 degrees. All right, so our next definition, and we're going to get a lot of use out of this guy, is what is called a unit circle. So a unit circle is a circle with radius 1 whose center is at the origin. So if we think all the way back to chapter 1, we know that the center of a circle is located at the point h, k. And in this case, since it's at the origin, that means our center is the point 0, 0. By definition, a unit circle has radius 1. So if our radius is equal to 1, that tells us r is equal to 1. This equation of a circle was x minus h squared plus y minus k squared is equal to r squared. So if we substitute in all of our values, we have x minus 0 squared plus y minus 0 squared is equal to 1 squared. And this simplifies to x squared plus y squared is equal to 1. So this is the equation of the unit circle. So we can use the unit circle to help us define some trigonometric function values or trigonometric ratios. So now imagine we have a point x, y on the unit circle. Well, if I draw a segment from the origin to any point x, y on the unit circle, well, since we know that the radius of this circle is 1, that means this distance is 1. And if we look at the sides, we can make a triangle, a right triangle specifically by doing this. So this side is going to have length y, because that's the y coordinate of the point. And this side of the triangle is going to have length x. We can talk about our angle theta, or our rotation from the positive x-axis. So theta is called the reference angle. the reference angle is always an acute angle measured from the x-axis. So we do have to be a little bit careful. So now imagine I had some other point here on my unit circle. Then I would have this would have length 1. So according to this definition, it says my reference angle is an acute angle measured from the x-axis. So first thing we want to note, this is not going to be always the same angle as the angle of rotation, because we're not measuring from the positive x-axis. So I'm not going from here to here. My reference angle is always measured from the x-axis, and it's always an acute angle. So here, this would be my reference angle. So we note that the reference angle is always acute, and remember that means it's between 0 and 90 degrees, so it can't be bigger than 90. So if we're in quadrants 2 or 3, our reference angle is going to be measured from the negative x-axis. If we're in quadrants 1 and 4, our reference angle is going to be measured from the positive x-axis. So we have to be a little careful with that. All right. So let's go ahead and use this circle to define our trigonometric functions. So if we go back to this circle, or this reference triangle in quadrant 1, if we think back to last time, what's the definition of the sine of theta? Well, sine theta by definition is opposite over hypotenuse. But our hypotenuse, since we're on a unit circle, is 1. So that gives us that on the unit circle, sine theta is equal to just y. Similarly, if we were to figure out, well, what is the cosine of theta? Well, cosine of theta was adjacent over hypotenuse, so that's going to give us x over 1, which gives us that the cosine of theta is just going to be the value of x. Lastly, we can do tangent, and there are a few ways we could do that. So the tangent of theta is opposite over adjacent. So that's going to give us y over x. So on the unit circle, we get the following definitions for our trigonometric functions. So we have that sine theta is going to be the y value on the unit circle. The cosine of theta is going to be the x value on the unit circle for the rotation. And tangent theta is going to be y divided by x. All right, so let's go ahead and take a look at our next example. So let's see if we can use our unit circle to find some of these values. Well, I'm going to do the first one, and then I'm going to have you guys do the next two. So we want to find the tangent of 45 degrees. So 45 degrees is right between 60 and 30, so right here. So I'm just going to take a clip of the first quadrant of my unit circle. And I want to find the tangent of 45 degrees. So I look at my unit circle here, and I'm going to have my 45 degrees is right here, and that corresponds to this ordered pair right here. And we have our x value and we have our y value. So we determined, based on our unit circle, that tangent was opposite over adjacent, so tangent was the same as y over x. So to find the tangent of 45 degrees, we take y divided by x. Well, our y value is the square root of 2 over 2, and our x value is the square root of 2 over 2. And anything divided by itself will always be the value of 1. So we get that the tangent of 45 degrees is 1. And we can verify that with our calculator. So if I go tangent 45, my calculator gives me this. Why didn't my calculator give me 1? So the most common error that happens when our calculator is giving us the wrong values is if our calculator isn't in the right mode. Well, notice I press my mode key. My calculator is in radian mode. We'll talk about radians later, but it's giving me the wrong value because I'm putting in 45 degrees, so I need to tell my calculator that I am using degrees, so I change to degree mode. And now if I go tangent of 45 degrees, my calculator does give me the correct value, which is 1. So we need to be a little bit careful when using our calculator to verify some of our solutions. All right, so to calculate the other values, we have cosine of 60 degrees. So cosine by definition is x, so we go to 60 degrees and we get that the cosine of 60 degrees is then going to be 1/2. And the sine of 30 degrees, so 30 degrees is here, and sine is going to be y, so we're going to get our 1/2 from this. All right. So now we want to ask ourselves the question, well, what if the terminal side is on an axis? Well, our unit circle can be used to answer that question. So if we look at our unit circle, so if our terminal side is on an axis, that's when we're at 90 degrees, 180 degrees, 270 degrees, or 360 degrees. Well, we can just use our regular definitions if we're on one of those sides. So, for example, then, not in blue, we have our 90, our 180, 270, and 0 or 360, because 0 and 360 are coterminal. So if I go to 90 degrees, well, the ordered pair of that point is 0, 1. So then we would have the sine of 90 degrees. Well, sine is the y coordinate. So the sine of 90 degrees is going to be 1. We would have that the cosine of 90 degrees is going to be the x value. So that's going to be 0. And then if we had tangent of 90 degrees, well, that's going to be y divided by x, which would be 1 over 0, which is undefined. So on some of the axes, we're going to run into some of our trigonometric functions being undefined. So similarly, we could do the same thing at 180, because at 180 our coordinates would be negative 1 and 0. At 270, we would have 0 and negative 1. And at 0 or 360 on the unit circle, we're at 1, 0. So just because we're on an axis, the terminal side of our rotation, it doesn't change anything. We can still just use our ordered pairs to calculate our values at those points. All right, so let's take a look at our next example. So example number 3, we wish to find sine theta, cosine theta, and tangent theta for a terminal side that contains the point -3, -4. So if I do a sketch, -3, -4, -3, -4 is going to be down here. So then that would mean if I were to make my triangle, that this distance is going to be -4, and this distance is going to be -3. And my reference angle is going to be right here. Because remember, the reference angle is always an acute angle as measured from the positive x-axis. All right, so now if we want to calculate the sine of theta, we know by definition that sine theta is opposite over hypotenuse. And we can't just use the y value this time because this is not on the unit circle. So to find the hypotenuse, we're going to use the Pythagorean theorem. And that would give us that c squared is equal to a squared plus b squared. So then that gives us c squared is equal to -3 squared is +9, -4 squared is +16, and 9 plus 16 is 25, and the square root of 25 is 5. So that would mean then that the hypotenuse would be 5. So then sine theta would be opposite over hypotenuse. So that's going to be -4 over 5. And then we would have the cosine of theta would be adjacent over hypotenuse, which would be -3 over 5. And then lastly, we want the tangent of theta, which is opposite over adjacent. So that's going to be a -4 over a -3. And a negative divided by a negative is a positive. So the tangent of theta in this case would be positive 4/3. All right, so the last thing from this section is we want to part on the following question. If we know the value of one trigonometric function, can we find the values of the others? So basically, the question is saying, if I know the value of one trigonometric function, is that enough information to find the value of the other trigonometric functions? Well, let's see. What if I knew that the tangent of theta was equal to negative 1/2? Well, we know that the tangent of theta is the same as opposite over adjacent, which is y over x. This gives two possibilities. So if we know that y over x is equal to negative 1/2, we could have the following. We could have negative 1 over positive 2, or we could have positive 1 over negative 2. So that would correspond to the two ordered pairs, 2, negative 1, or the ordered pair 1, negative 2. And we notice then, if we were to draw a picture, 2, negative 1 is down here in quadrant 4, and 1, negative 2 is back here in quadrant 2. I wrote that incorrect. Y over x. Yeah, that guy's backwards. I was like, something is not right there. So y over x, so negative 2 and 1. Much better. So negative 2 and 1 would be right here. And each of these would then have a different reference angle. So that would be my reference angle, and that would be my reference angle. But each of them would have a different measured angle. So the answer is no. The value of one trigonometric function is not enough. So we need either 1, the value of another trig function, or 2, the quadrant of the angle. So the minimal set of information we need then is either one more trigonometric function or just the quadrant that the angle is in. And if we have either of those two things, that's sufficient to determine the values of those trigonometric functions.